frozen and you write on the Promethean board, does it recognize it on the computer?
Yeah, yeah, totally.
John, cool.
Oh, what's going on here?
Oh.
Oh, my God.
Just
We
embedded
can see where
as-
people got there's me, I didn't.
Okay, much better. Okay, so like I say, there's an easier. We're gonna uncover an easier way of doing this. What seems to be a pretty hard problem. All right, so here's how we're gonna do this. I think I have some kind of fancy. Oh, look at that. There we go. Okay, so we can kind of go down this. Oh, that's the wrong one. My goodness.
That's that one.
No, keep going. There you go.
That's the one I want.
There, yeah, do that there.
Okay, so let's look at something here. I just want to go back to a kinematics problem, or kinematics equation. We know this one, right? This is the one that doesn't use time. Okay, so that already betrays a little bit of our approach to this, is we're not going to bog ourselves down with trying to deal with time stuff. So there are going to be certain situations where, you know, we're going to have to find workarounds, or worst case scenario, go back and do this the way we have in the past, right? But this is the one that says the final speed, it's not velocity, right? That's not a vector quantity. The final speed squared minus the initial speed squared equals 2 times the acceleration times the displacement. Kinematics equation number 4. We've used it a ton, right? Going all the way back. Okay, let's flip this around for convenience and put, you'll see why in a second. Let's just flip it around. So we're going to exchange the sides that the expressions are on. And let's take into account something here. We know that F equals ma, right, for us. Technically, F equals delta P over delta T. But remember, we had that discussion about a little white lie I told you about F equals ma. Well, it's fine. It's fine unless you're dealing with really weird relativistic situations where we're traveling close to the speed of light, which we're not in any of these problems, right? So F equals ma is fine. So then if we solve that for A, would you agree that A equals F over M? Right? So we're going to make that substitution. Now there's one other thing we probably want to look at here. If we're saying that, if we're using this kinematics equation where we're relating the final velocity, or final speed and initial speed to acceleration and displacement, then we're assuming that the acceleration is in the direction of motion, right? Doesn't that make sense? I mean, that's the acceleration we're talking about. If an object has some initial speed and we push on it, and it speeds up, and then at the very end of this, we figure out how fast it's going. Well, it accelerated along its direction of travel, right? So just to remind us then, that when we relate this to force, we're really thinking about the parallel force, right? If there were some other forces acting, they're irrelevant, right? Like let's just say, for example, that somebody, how do I do this? Let's say that I was sliding along the ground and somebody was pushing me at an angle. Well, the only part of that force that's going to make me go in that direction, that's going to cause the acceleration that we're talking about here, right? That's going to change my speed, is the part of the force that's pushing me in that direction, right? Not the part that's pushing me into the floor. Agreed? Okay, and we'll come back and revisit that in a second, and then that'll even be clearer, I think. But so I'm just going to put this parallel subscript up there to remind us that we're really talking about the forces in the direction of motion, right? Okay, so then let's make that substitution where we used to have an A over here in our kinematics equation. Let's replace that with force divided by mass, right? What's that give us? Well, it gives us something pretty messy looking, right? Instead of the A, we've got this. Okay, well, let's do something with that. Let's reorganize a little bit. This is just 2 times F times displacement divided by M. But let's put the force times displacement, let's multiply those first, because we can change the order, right? And let's group the 2 over M together, okay? And then we're going to get rid of that from that side. I'm going to multiply each side of this equation times the reciprocal, times M over 2, okay? So that's going to cancel it from this side, right? What do we end up with on the other side over here? And this is a lot of math, but when we're done with this, the results are amazing.
M happens.
So we're going to multiply both sides by M over 2. Right, that cancels the 2 over M on the left side. And then we get something like that, don't we? There it is. If I just rewrite that, if I distribute the M over 2 to both of those two terms, this is what I get. I get 1/2 times M times final speed squared minus 1/2 times M times initial speed squared. That's pretty amazing. That must mean something, right? So we come up with an equation there. The force in the direction of motion times the displacement through which that force acts is equal to 1/2 mv squared minus 1/2 mv naught squared, right? That 1/2 mv squared must be something significant, right? That must be, because think what we did there. Let's just say it started off at rest. So let's say the initial speed was 0. I pushed on this thing and I pushed through a certain distance and then I let it go. And when I let it go, it was moving with a certain final speed. I did something to that though, right? The force that I applied, in a manner of speaking, I invested it into the object and I gave it some motion, right? I had to do something though. I had to push on it to make that happen, right? Anybody know what that quantity is that we gave to it?
100 newtons, 110 newtons.
Well, what do you think this is? What is this? Anybody have any idea what this 1/2 mv squared thing is? What do you think? Any idea? This is a term we haven't thrown around yet, but it's a really important one in physics. Let's say I want to do something useful. I want to knock a hole in that wall, right? So I'm gonna push on this object. The floor is all greased up and it's slippery, and I'm gonna push on this big stone object and get it sliding across the floor so I can do something useful and knock a hole in that wall, right? How am I gonna knock a hole in the wall?
I'm not sure I understand. Can you get more physical
You want a demonstration?
representation?
Yeah. Okay. So if I just push the object up against the wall and let it sit there, it's not gonna do anything, right? How's it gonna go through the wall? It's gonna go through the wall because I gave it some motion, right? Well, what do you think?
Oh, yeah, momentum, because MP.
Okay, mv is momentum. That's true. That's true.
So we can relate
But this
that.
is a little bit different. So it's not necessarily momentum that we're giving this object, right? Let me give you another analogy here. I could bake a cookie theoretically. That sound good?
Theoretically.
It's after lunch. How can that sound good? You guys should be full. So I could theoretically bake a cookie if I had if I did this just right. So if I threw some cookie dough really fast, and when it splattered against the wall, let's put our phone around this. I want you guys to really get on this. So when it splattered against the wall, if I caught it in a receptacle, so it couldn't just splatter every place, so it landed in there and stuck in there. If I threw it fast enough, I would actually cook the cookie. Ah, how come? Yeah, because it had all this energy coming in, right? And when it hit the wall and was stuck in this little receptacle and it stopped, all that energy that it had moving through the air that, we'll give it a name in a second, was released as heat, and it cooked the cookie. And that really would work, technically. Might be very
How fast would it have to be?
Well, we'll work on that part later.
Okay.
Well, that's a good question. Maybe we better address that
We need to
later.
answer that.
Just do a lab.
Yeah,
Thank you.
that'd be a good
Can
lab.
that be the rest of like our school year?
You're just
a lab?
trying to get cookies to
Yeah.
cook by throwing them against the wall. It'd have to be going pretty fast, I'll tell you that.
So figure out how fast with some experimentation.
Yeah.
So what do you think this is then? What do you think this quantity is?
Joules.
It's measured in joules. It is. It's measured in joules. And it's called kinetic energy. Okay? What does kinetic mean? Movement. It's the energy of motion. So when I pushed on this object in physics, I literally did work on it. That's what we call that. If I apply a force through a distance, I'm doing work on the object, and I'm giving that work. That work is being converted into kinetic energy that the object now has. Right? I had to do something. I had to burn up some calories. I had to use my muscles to push this object through with a certain force through a certain displacement, right? And so all that energy that I'm expending to push this thing now gets invested in the object, which carries that energy with it in the form of kinetic energy, right? So So that's kinetic energy, right? Okay, so what do we call this stuff? So look at this. Then this says that force times displacement is equal to my final kinetic energy minus my initial kinetic energy, right? Well, final minus initial, that's always just changing. We could summarize that by saying delta KE, right? So this quantity right here that I did, that's called work, and we'll talk about that in a second. The work that I applied, the work that I did in pushing this object was completely converted to the change in kinetic energy of the object. If it already had some speed, well, now it's going to have more. If it didn't have any speed, well, now it's going to have some, right? Okay, so that's called the work energy. Well, it's actually, it's one way of expressing the work energy theory. We'll get more detailed later. Okay, we can go one step further with this. Because what is this F parallel thing, right? We said that that's only the part of the force that's acting in the direction that the object is moving. The rest of the force is really wasted, right? If I push, let's look at this. If I push down, I've got an object that I want to slide across the desk here. So if I push straight down on this thing, how much work am I doing? How come?
Because it's wasted.
Well, you can tell I'm not doing any because it didn't change its motion at all, right? But if I push it a little bit of an angle, I can accelerate it, right? Now, some of that push was useful, right? But some of it still pushed it into the desk. If I push it in this direction, though, I get the most acceleration for my push, right? Because then all of that force is useful, and it's all accelerating it along the direction of motion. So what if I do push at an angle like this then, right? If I push at an angle like that, and I'm pushing with a certain amount of force, I have to know how much of that is being applied in the direction of the displacement. So all I've got to do, so there is one little vector part of this, but it's not much. If this is the direction in which the force is acting, and this is the direction of the displacement, then I just want to find the component of that force that's acting in the direction of the displacement. So if that's the angle theta between the two, and that's how we define theta, it's the angle between the direction of the force and the direction of motion. How would I find that component of force? If I break that into components,
Cosine.
yeah, it's cosine, isn't it? This is what we might call F parallel, and that's what we might call F perpendicular. And the perpendicular force didn't do anything, right? It didn't change the speed of this thing at all. It wasn't pushing in the direction it was moving, right? So F parallel is really just equal to F cosine theta, right? So that's how we get from there to here, right? So now we ought to be able to go back. We ought to be able to go back and do that problem again much more easily, shouldn't we? If we just take this one formula, let me just grab this thing.
I'm glad you heard. It's okay, I don't need her credit to give me the
It's getting kind of rude here.
Okay, so what about that? So if we're going to use that formula, let's just add the right information to this picture that we need. So what's the angle? 40 degrees. What's the magnitude of the force?
100.
100 newtons. What's the mass?
20.
No, 100. 100. What's the initial speed?
1 meter per second.
V naught is 1 standard units, right? Okay, so we're trying to figure out how fast it goes after we're done with this, right? So do we have all the pieces that we need? Oh, and we're pushing it through what displacement? 6 meters. Okay, so we're pushing it through this distance right here, we'll just call 6 meters from there to there, okay? So we know F, right? Actually, that's supposed to be F parallel though, right? Oh, no, never mind. It is F cosine theta. Never mind. We have it written down. So we have F, we have theta, we have the displacement, we have the initial speed, right? We have the mass. The only unknown is final speed. And that's a pretty easy problem to do, isn't it? Right? If I want to solve this thing, what are the steps I would go through to solve this thing for V?
Solve V.
Add that to the other side, right? And then what do we get? So if I add that, let's put this on the left side. I get 1/2 mv squared equals, so I'm gonna get F delta D cosine theta plus 1/2 mv naught squared. That's all stuff I know.
Yeah.
And then what do I have to do to both sides to get the v by itself?
Square root.
Okay, multiply by 2 over m and square root it, right? But then I just put all that in my calculator. One step. There's nothing to do, right? That would have been a many step problem if we had to use kinematics, vector resolution, we had to find it, right? And that would have been a lot going on there. Okay, but this is pretty simple. So we just end up with, if I solve for m, we'll put this all in our calculator. 2 over m times all that stuff. Oops, that's a v, not an m. Times f delta d cosine theta plus 1/2 m v naught squared. And then I just have to square root it, right?
Not Jaws.
And I got it, okay? So we could throw all that stuff in the calculator real quick. Let's do that.
That was like.
Yeah, do you not know the Jaws thing?
Do you guys remember?
Backwards, okay?
You remember those? You remember them all. Right? You remember the quantities.
Yeah.
So am I in degrees mode? Yes, I am. Always check. So we've got 2 divided by m. I'm gonna please River here and do the fancy fraction template
Yes,
like he always
thank
likes
you.
to do.
Consistent.
So
Yeah, you forgot the
two-
square root on the outside.
I forgot what?
The square root.
Oh, I already did, didn't I?
I remember changing to degrees.
Square root.
I'm telling you, the fraction thing is gonna help, like, your students who don't know crap about math, visualize it.
Everybody in here knows math pretty well. So I
No,
wouldn't be
yeah.
too worried about it.
Well,
Okay, so 2 divided by m is 100, right?
yes.
Okay, times the quantity. Force was 100 newtons, right?
Yeah.
So F is 100. We'll just suppress the units here to be lazy. 100 times delta D was 6 meters,
Yes.
right? So times 6 times cosine of 40, right? Plus 0.5, let's put in 0.5 for half. 0.5 times m, it's 100, times
1.
But
One
we don't need to do it, so we can just, well,
square.
you add one.
Oh, I did, you're right.
We can just delete both of it, really.
Times 1, and it's 1 squared is 1. I can just stop there. Everybody agree? Okay. Do I
Final
need to
parentheses.
Put squared, put squared, put
final
squared.
parentheses?
Hey.
Okay. And I didn't put the 1 squared just 'cause I don't need to, it's 1.
Well, you also don't need to put the one at that point.
You're true. Yeah,
So,
true. Good point. Okay, so if I hit enter, we get that. How about
Sounds
that?
about right.
Okay, that's how fast it's going. Okay.
Yeah.
Isn't that amazing? Super easy, right? Super easy, okay? All right, so what about, I got another problem for you then. You guys think you're pretty smart, and you are.
No, that was all River.
You didn't do anything.
Exactly.
Okay, what about that? What about that? So the picture is worth 1,000 words, right? So we got this skier skiing down a mountain.
I like the
So let's see, starts from rest. How fast is she moving at the bottom of the hill, assuming she liberally applied slippery and wax to her skis? That's trademark, by the way. So she's going 50 meters down the hill, okay? 50-degree angle, starting from rest, 0 initial speed.
How much
How
does she
fast?
weigh?
Say it again.
How much does she
Yeah,
weigh?
what's her kilogram?
I
Does she
didn't
have
give
a-
that to you.
Does she have a swim cap on?
Does she have a swimming cap?
She is wearing one of those fancy Olympic ski suits, so and that's also slippery.
Did she make sure there wasn't trees at the bottom?
Can
Of course,
we, like,
of course.
Can we have?
Okay, so anyway.
What if a bear walks in front of her?
Yeah, whatever. Okay, so what about this? So this also would be a little bit of an issue for us to do. We could have done this problem before, but it would have been reasonably complicated, right? Okay. Well, let's see some ways we can approach this. Now I'm going to leave the problem for a second, and I want to ask you something. So let's say I'm going to take this.
Sure, Max.
no, I'm gonna take this 1 kilogram mass, which I happen to have here, which is nice. We got a 1 kilogram mass, and I'm gonna do some work on it, right? We said that work, from the last equation, right? Work is what I get when I apply a force through a displacement, right? Okay, so the work is equal to the parallel component of force, meaning the force in the direction of displacement, right? Times the displacement. So this is all I'm gonna do. I'm gonna take this thing and I'm just gonna, let's say I'm gonna pick it up at constant speed, 1 meter, and set it on a shelf. Okay, did I do work on it?
Yeah.
Yes.
Okay.
Because it didn't accelerate.
Okay, it didn't accelerate, but I definitely applied a force in the direction of motion this time, didn't I? Right? Okay, what was the force I applied? If this has a mass of 1 kilogram, roughly, just round, what's the force? What's the weight of this thing?
1,
No.
2.
9.8.
Come on now, 9.8, so we'll call it 10,
Oh.
right? MG, right? So it's got a weight of 10 newtons, so to support this thing, it's not accelerating. So there's two forces acting on this weight. There's the downward force of gravity, which is 10 newtons, and my upward support force, right? And if it's not accelerating, the net force on this thing is 0, right? Just moving at constant speed. So I'm applying upwards a force of 10 newtons, and I lifted it through 1 meter. So how much work did I do? It's easy. What's the force times displacement? 10 newtons times 1 meter, right, is 10, and the units are joules. Okay, now why is it not a newton meter? In this case, we call it a joule because joule is the unit of energy, right? And the work that I'm doing to this thing is related to the energy that I'm giving it. So we always measure work and energy in terms of joules in physics. Yeah, it's just a newton meter, right? But just different contexts, so we say different things, right? Okay, so now if I'm doing 10 newtons or 10 joules of work on this thing, but its speed didn't increase, what's going on?
You are applying the same force.
I'm setting it on the shelf, but something changed. It wasn't the kinetic energy though, because it's not moving, right? Pushing this thing up and setting it on the shelf. Now, I don't want to drop this thing because it's pretty heavy, but like let's say I drop, pretend this is my 1 kilogram object, and a big spider walks underneath it, so it lands on the spider and squishes it when I push it off the shelf. It did some work for me, right? It crunched that big, it was a big spider. Thank you. Thank you. I wake you up a little bit, that's good. Okay, so what did I do then? I did something useful because before I couldn't have done that. When the thing was sitting on the desk, that's not gonna affect the spider, it's just gonna bump it. But when I picked it up and put it on the shelf, if I give it a little balance it there, if I gave it a little nudge, it accelerated down and splat.
It's
Right.
potential energy.
Ah, okay. I did something different, didn't I? I stored it. Instead of giving it to it directly as kinetic energy, I gave it to the system as potential energy, which was stored, which it gave back eventually as kinetic energy, right?
We all have a crazy amount of potential energy because of the distance between us and the center of the Earth.
Okay, so, well, that's a really interesting question. So what is the energy? Now, so I picked this thing up and put it on the shelf.
Yeah.
So we could say that its stored energy is 10 joules.
Sure.
Okay, but it's 10 joules is, we have to be very specific about that, because if I were to convert all of the mass in this 1 kilogram object into energy, into pure energy, that would be enough energy to,
Blow the sun.
it'd be enough energy to, for example, well, we could do a calculation, but I'm gonna estimate it would be enough energy to lift, let's say, I'm gonna say about 500 million tanks off the ground, say a meter or something. I could be way off, but it's gonna be a tremendous amount of energy, right? And so when we say, it's a good question, and we say it's got 10 joules of energy, well, that's a little bit hokey. It doesn't have 10 joules of energy. It's got 10 joules of energy compared to where it started, right? So the amount of energy invested in this thing is arbitrary, and it's a huge amount. We'll talk about how I got that number later. Einstein helped us out with that a little bit. But that's not the point here. The point is, let's define something like, let's just say that, let's call the energy 0 right there, because it's at rest on, maybe pretend this is the floor, okay? So I pick it up and I put it on the shelf, and now relative to its initial position, we've given it an additional 10 joules of energy, right? And when I let this thing go, it's giving back just that 10 joules, right? Okay, so how much energy did we give it? Let's try to quantify this a little bit. If we let's think about, we know work is just force times displacement, right? So work equals the parallel component of force, so the force in the direction of motion, times displacement, and you guys already did the math on this. The force was 10 joules, right? Okay, but what caused the force? What was that force equivalent to? How did you get the 10 newtons again? Okay, but I told you one thing about
Mass
it.
times gravity.
Mass times gravity, right? Okay, so really the force was equal to mg, wasn't it? Right? Okay, so the force became mg, and let's say that the distance we picked it up, being as it was vertical, let's call that h. So that's the kind of force that's kind of energy that we gave it, right? Well, that we're going to come to call that this part right here. Gravitational potential energy. We have to be specific and call it gravitational potential energy because it's not the only kind of potential energy. Somebody tell me another kind of potential energy.
Static.
Somebody tell me another kind of potential energy. Are you sure? No.
Magnetic potential.
True. What's one that you use every day, probably?
Food.
Food. Yeah, chemical potential energy. You eat food, and that's broken down in your body and metabolized, and it's a lot of energy stored in food. There's another one that you pour in your gas tank, some liquid potential energy. You pour in your gas tank, you probably pour a ton of it in your gas tank. Right? Gas would be another form of stored chemical potential energy. There are other kinds, even of mechanical energy. Like if I take a rubber band and I pull it back and let it go, I can shoot it across the room because why? I'm storing some energy in the elastic stretch of that. So that's elastic potential energy, right? There's a lot of different ways we could talk about different types of potential energy we could talk about, but for our purposes, this is the one that's really interesting, is gravitational potential energy, right? Okay, now let me try something else on you here. Let's say that I'm going to do this instead. Instead of moving this thing up 1 meter, I'm going to move it up 1 meter and over 1 meter in a diagonal line. So now I'm going to do this. I'm going to set it on this shelf over here instead. How much work did I do?
More.
Half.
What do you think? Raise your hand if you think I did more work. Raise your hand if you think I did less work.
No, it's an hour.
Oh,
I think
okay. Anybody have a different answer?
It'd be the same.
Same amount of work is the right answer. How come? How come?
You're not really changing the amount of work, you're just like changing the location. Like,
Okay, so in this case, in what direction am I really applying the force here? I'm applying it upwards, right? Because the thing is moving at constant speed, so I'm not accelerating it sideways. So this is the force vector, right? The displacement vector is in this direction though, so it's like that. Okay, well, what's that tell you then? If we go back to our true definition of work, we know that, yeah, it's the cosine theta part, right? So we know that, yeah, parallel component of force times displacement, we could write that in a better way by saying F delta D. So force times displacement times the cosine of the angle between. And really, there's two ways we could think about that. The way that we talked about previously that mostly you think about is we could say it's the component of force acting in the direction of displacement, but we could also lump the cosine theta with the displacement, right? And we could say in this case that, yeah, I'm applying this force upward, but the displacement is at some weird angle. How much of that displacement is really along the direction of the force? Only the 1 meter part, right? Does that make sense? Everybody see that? Right, so yeah, I moved this thing 1.414 meters, right? But I only moved it 1 meter against the force of gravity. So that's the movement that actually did work, right? If I take this thing and move it sideways like this, how much work am I doing? Zero. I'm doing zero work, because it's moving at constant speed, so its kinetic energy is not changing, right? The direction of force is up, but the direction of displacement is sideways.
Yeah,
So-
but if you're going perfectly sideways, aren't you doing work in that direction then?
Okay, but as long as, okay, now what you guys are thinking is, okay, I had to start this at some point, so I have to I have to do some work to accelerate it. But let's just only look at the part of the movie here, start it right now. So I'm just moving it sideways, stop, now maybe I'll stop, but if I stop the movie, during the course of the movie, the amount of work that I did on this thing was zero. Because the force and the displacement were at right angles, right? Either way you look at it, how much force was acting in the direction of displacement? None. How much displacement was acting in the direction of force? Zero. What's the cosine of 90? Zero, right? See what I'm saying? Okay. You getting it? Isn't this weird? But it works. It works. Okay, now let's do one other thing here. I don't want to do too much today, but I can't resist. Let's do it. Okay, I'm not going to write any of this stuff down. We'll come back to this again later.
recording this?
I am recording this, yes. Okay, now let's calculate what are all the forces acting on this object. This is just,
Gravity.
okay, gravity and
Your
my hand, right? Okay, so the normal force of my hand. So there's two forces acting, my hand and gravity. Let's calculate the work done by each one. When I pick this thing up and put it on the shelf. So we already said if I pick it up 1 meter and put it on the shelf, I did 10 joules of work, right? How much does gravity do? Okay, let's think of, let's see if we can figure out why. When I pick this thing up, the displacement is in this direction, right? In what direction is gravity acting? Oh, so the angle between the two vectors is what? There down to there. 180, right? What's the cosine of 180?
-1.
-1, right? Okay, now the component of displacement in the direction of force this time is -1, because the force is acting in that way, and I actually moved it against the line of force, gravity, right? So I did 10 joules, gravity did -10 joules, so we might say that the net work, and that's a word we'll use, the net work done on this object is the work done by all the forces acting on it. What was that? Zero. Okay, what else didn't change about this thing? True, but in terms of energy stuff, the potential energy changed, but the kinetic energy did not, right? Suppose that's an accident. No, it's not. It's not an accident. Let's do one other example. Let's look at something like this. Let's take the example where I'm going to pick this thing up, but I am going to accelerate it this time. I'm going to apply a force of 20 newtons to this 10 Newton object, right? Force of gravity is 10 newtons and my force is 20 newtons, okay? How much work do I do in picking it up to the level of the shelf then? Twice as much. 20 newtons times 1 meter is 20 joules, right? Agreed? How much work does gravity do? No. Negative. What's the force of gravity acting? -10. Good. And the displacement is 1, so it's just like it was before, it's -10, right? Now what's the net force acting on this object? What's the net, the net work that was done on the object? I did 20, positive 20, gravity did -10, those are the only two forces acting. So the net work is 10 joules, right? Okay, let's make a little calculation here. If we're gonna go back to the old school physics we've been doing. The net force acting on the object was positive 10 newtons, right? I was pushing up with 20, gravity was pushing down with 10. Everybody agree? Okay, so then if we want to calculate the acceleration, Newton's second law tells us that net force equals ma, right? So acceleration is just equal to net force over m, nothing new there, right? So that's going to give us, we said it was 10 newtons divided by 1 kilogram equals 10 meters per second squared is the acceleration. Everybody agree? Okay, let's figure out how fast this thing is going at the end of that journey then. That's not a big deal. We'll use, we can just use, let's see, bottom one really, couldn't we? right? Okay, we know the initial velocity is 0. The final velocity is what we're looking for. We know the acceleration is 10. And what else do we need? Displacement. Delta D is positive 1, right? So we end up with v squared minus 0, right? Minus v naught squared equals 2a times delta D. Okay, so v squared equals 20. So v equals the square root of 20, which is about 14.14-ish, okay? So that's my final speed, right? Let's calculate my final kinetic energy, right? The initial kinetic energy was 0, wasn't it? Everybody agree?
Where did you come with the 14.14?
Square root of 20.
That's not even close though.
It's not?
14 times 14.
Oh, no, hang on, what am I saying? Square root of 20. Where did I get that? Square root of 20.
And
What was I thinking?
4.47.
Yeah, it's like 4.
Oh my gosh, what was I doing?
It's 200.
Square root of 2, 1.4 times.
Yeah, 200.
Yeah, that's
Square root
not-
of 200.
yeah, that's
Yeah,
what-
it's the square root of 200. Yeah, no
Yeah.
wonder, that's square root of 200. So what is it about? Somebody, it's right
14.47.
here. What is it?
4.47.
4.47, there we go. 4.47 meters per second. Ooh, okay, so that's my final speed. So let's calculate my final kinetic energy, right? I started at 0, right? Started at 0, and I end up with this speed. So my final kinetic energy is 1/2 times m times v squared. Well, what's v squared? V squared is 20, right? I square rooted it, but if I just square it again, I'm going to get 20. So 1/2 times 1 times 20 equals positive 10. Huh. Interesting. Interesting. That was the net work done on this thing too, right? Not a coincidence. The net work corresponds to the change in kinetic energy, right? Think about it this way. Think of it in terms of an energy budget. I did 20 joules of work on this thing, right? But 10 joules of that work, in the absence of any gravity, if we were in outer space and I did that experiment, I would have invested all of my work into the kinetic energy of this thing, right? It would have left with 20 joules of kinetic energy. But there is gravity. And so if I keep track of the energy budget, yeah, I invested 10 joules of that just to give it the gravitational potential energy to get here, right? Does that make sense? 10 of it was lost working against gravity. The extra 10 that I applied above gravity is what was left over to invest it in the kinetic energy of this object, right? Does that make sense? That's pretty cool, right? So then if we look at this problem right here, we ought to be able to do this problem much more easily, right? Because all we need to know here is, really, all we need to know is, doesn't matter the direction that this person moved, if there's no friction involved, right? What's the only force that's acting in the direction of motion here? Gravity, right? So only gravity is going to do work on this skier. No other force is, right? So if you think about this then, we should be able to convert, when they started up here at rest, did they have any energy? Jonathan Jennings, did they have any energy when they started up here at rest?
No.
Yeah, they did.
Yeah, they did.
What was it?
Kinetic.
Potential. Potential. There we go. Potential. There we go.
Potential.
So they had all this energy stored as gravitational potential energy, this girl did. When she skied down the hill and she gets to the bottom, her potential energy is gone, but what has it turned into? Kinetic. So this is super easy, right? All we'd have to do, if this is a 50-meter long hill, and that's a 50-degree angle, we just need to know how high it is, right? Does that make sense? How high it is so we can calculate MGH. And when we get to the bottom, that's going to equal mv squared, 1/2 mv squared. Right? How much time we got?
1 minute.
Oh, okay. So we're done.
Did it.
How cool isn't that just so cool?
That's cool stuff.
Oh man, you cannot think that is not cool.
Well, you say that.
No.